Hello guys, how are you today? And let's wait for 2 more minutes because we are supposed to have around 40 of you here. Okay, thanks. Let me start the recording. Yeah, I think we have started the recording. Start. Yeah, hello everyone. This is week 5, and we are going to have the first hour together, the 3 groups, and we will explain to you some basic ideas, concepts, and knowledge about the Envi simulation and how to interpret the output files. And in the second hour, you will join the individual group with your own tutor. And Kai's group and Samira's group will join the Blackboard Collaborate, and my group will stay here. Yeah, it's just for the first hour, we will explain to you all together about some basic concepts. And we will explain to you first about, let me open this, the numerical model about the climate, and what is the boundary condition, what is the initial condition, and what is the logic behind the simulation. And Kai will explain this part. Then I will introduce you about Envi output, what kind of output you will get after you finish the simulation, and what kind of information specifically is included under each output folder, and how do you analyze the different information, and what are the mandatory parameters to be analyzed in our assignment 2, and what are they optional. And I will show you some examples about the analysis. And then we will have the very last part as the highlights. We hope to explain some key information about the simulation settings. You can choose different different forcing methodology, but we will let you know how to what is the source of the climatic data and how do you choose the different simulation methodology, and then the correct date and time for simulation. We just want to make sure and everything is correct before you move on. This information are provided also in assignment brief, and you may double check. Yeah, and I think we can, now we have 28 and we can start from the very first part. And I will ask Kai to share the screen. I will stop sharing.
Can everyone see my screen?
Yes.
Okay, let's start. Today, I'm going to introduce some important concepts about numerical climate models and how they're related to your Envi simulations. You have been learning Envi for several weeks. I think most of you have gone through all the procedures that Envi finish to finish a simulation. And here I have a definition for the numeric climate model. And numeric climate model is used to simulate the weather variation within a limited time duration in a limited space. And our Envi is also a kind of numeric climate model. So what you're actually doing in Envi is weather forecasting of that small area you have created. And basically, there are three types of numeric models, and there are microclimate models, and our Envi software is that microclimate models. And the model size in Envi usually is from hundreds of square meters to several square kilometers. And the next scale is mesoscale, and which is our weather forecasting used. We usually use this kind of model to predict like the bushfire forecasting or tornado or typhoon. And this image is a typhoon prediction, and you can see here. And the third type is the largest scale. It's a global scale simulation. They are often used in climatology research, and their time range is very large, as they can simulate from hundreds of years to thousands of years. And for all the numeric climate model simulations, the procedures are same. No matter you're using Envi or you are doing the weather forecasting, there are 4 steps. First is the pre-processing. We need to prepare the areas that we are interested for the model. In Envi, we finish this task by using the help of moment and space. We can create a space, and in the terminology called simulation domain. And after we create that simulation domain, we also need to assign the physical properties to all the elements in the model, like the reflection, the orbital. In the space, after you create a building or some vegetation, the materials and physical properties is automatically assigned, allocated if you do not change their default values. And you can check the detailed material properties in the database. And after you have finished your model, the second step is to providing its initial condition and boundary condition. I will explain later about what are these two things. And in Envi, you have to finish this with the help of Envi guide, and it allows you to input your own meteorological data as the boundary conditions. After setting up these things, and you have also need to set up physical suite and what kind of like cloud formation mechanisms you want to use. But in Envi, we don't need to set that. It will automatically completed by the software. It will evaluate what kind of physics your model is suitable to use. And then it's using this Envi core app to run the simulation. This is the physical engine. And after your simulation successfully gets the result, we use the post-processing tools to help you visualize. In AmiMat, we have these two tools. The Leonardo, it can visualize the distributions and the variation of the variable. And you can also use the Biomat to help you add some thermal comfort analysis. And the following pages explain you what are boundary conditions and initial conditions. Let's think together about one question. If we want, I have a cup of water, I put it in such an environment. If we want to predict the temperature of water after 5 minutes, what things we need to know? Apparently, the first thing we need to know is the temperature of the water when we put it in the environment, right? That's what we call the initial condition of that cup of water. And the second thing we need to know is what are the air temperature outside the cup, right? Because after we know that information, we can know how fast that the temperature will reduce in the cup. And that's what we call boundary conditions for the water. So this question can be regarded as the simplest simulation scenario. And the AmiMat actually is doing the same. What the model we have created is a cup of water. And that small area is not alone. It is surrounded by a larger world. The larger world will cast huge influence on the final result. And actually, the boundary conditions and the initial conditions will have different influence on the final result. Let me still use the same scenarios to explain. For example, let's first discuss about boundary conditions. Say these two scenarios. In the first scenario, the boundary condition is 0 degree. And the second scenario, the boundary condition is 10 degree. If I ask you to predict the temperature of the water after 5 hours, it's clear in the first scenario, the temperature will be 0. And in the second scenario, the temperature will be 10. So you can see in a long-term simulation, the final state of your model is decided by the boundary conditions. And that's how boundary conditions is so important in simulations. And for initial conditions, if we are still thinking the same question, what are the temperatures of the water after 5 hours? If the boundary conditions are same, but only difference is their initial condition, like the first, this cup of water has a temperature 100 degree, but the second cup of water has a temperature of 90 degrees. After 5 hours, their temperature will eventually become the same because they have the same environment temperature, right? So initial condition does not have much influence on long-term simulations. But if I ask you to predict the temperature of the water after 5 minutes, you can see in this time range, the temperature of the water probably have some difference. After 5 minutes, the temperature of these two cups will still would still be different, right? That's how initial condition influence our simulation. And in AmiMat, that's our whole model looks like. There's the ground, your buildings, and some empty space between the upper boundaries. And your whole model, your simulation domain, can be regarded as a block. And a block have 6 boundaries. And we have distinguished them in simulations. The upper surface is upper boundary and lower boundary. They are not that important as the lateral boundaries, because on upper boundaries, they are usually skies of tens of meters high. Almost there's nothing here, only clouds. So they won't cause many influences. And for the lower boundaries, they usually are the soil that beneath tens of meters. Is the temperature distributions there is uniform, as there is no airflow there. They also won't cast many influence on your results. But for the lateral boundaries, the atmospheric activity on the lateral boundaries are very active. The air flows in and flows out, and there are very active conduction and convection activities. So we have to give accurate meteorological data on the lateral boundaries to get a good performance of the model. And this link is more information of the lateral boundary conditions that used in EnviMat. If you are interested, you can click it to check. And after you have finished the model, you go into Envi guide to set up your simulation. The first thing it asks you to set up your meteorological boundary conditions. And it's using the words of
Sorry, there is some internet problem with Kai's computer. I think he can continue online, or you can wait for 2 minutes. Sorry about that.
Hi guys, I'm back. My computer just died. I just rebooted. Let's go back. Sorry about that. Let's go where we ended here. We are the meteorological boundary conditions in EnviMat. In EnviMat, if you open Envi guide and create a new simulation setup, the first thing it asks you is to how you want your meteorological boundary conditions to be, and there are different options. It allows you to use your own measurement data, and this is our standard procedure in a EnviMat simulation. You should measure your own boundary conditions and add it to your simulation. But unfortunately, in our class, we have no such no conditions to do that. So we can use the boundary. You can use the data from the nearest weather station as your boundary condition, and or you can just use the simple forcing, because in our simulation, what we are not very care about 100% accurate, but we are more care about the difference between different mitigation scenarios. So the change is much more important. So we don't have a very strict requirement for you, but you need to keep in mind if later after the class you want to use MMAT for other tasks, or you want to do a research in the MMAT, you have to set up your own meteorological boundary conditions. And it also allows you to set up upper and lower conditions as well. In MMAT, in MMAT guide, you can set whether your skies is cloudy or it's clear, but we don't ask you to do that. You just leave all the settings as default, and keep and make sure all your scenarios have the same boundary condition settings. That is very important, because otherwise one of your scenarios, if it has different meteorological boundary condition settings, it result is caused by that setting, is not caused by your mitigation measures that used in that scenarios, and you may get wrong conclusions. And next, MNGAT will ask you to allocate the initial conditions for the scenario for your simulation, as we just illustrate with the graph. Initial condition does not have much influence on your final result, but it will have certain extent of influence in a short period. And in this setup windows, you just need to make sure all the values are reasonable. You do not set some very absurd values like over 100 degrees or something. You just set values in the normal range. After when simulation starts running, these values can be corrected automatically. And since initial conditions has influence on a very small period, so when your model have started computing, you need to give it more time to spin up. That means let's say this curve, the black line is the actual air temperature we have measured of an area, and this red line is the temperature we have simulated. You can see here, because at the beginning, the initial condition, the initial temperature is different from the actual air temperature. So your model will experience sometimes to have some fluctuation, and it will adjust itself. And after a short period, everything becomes stable, and the influence of the initial condition is minimized. So that period time is called spin up time. In your simulation, we do not use the data in that range. And if your interested time period, for example, is 1 hour from 14 o'clock to 15 o'clock, and then you better start your simulation earlier than that. In my experience, you usually start your simulation 1 hour earlier before your interested time period. Let's say you can start your simulation at 13, and the first hour of the data will be discarded. You only use the data between 14 and 15. And next, we'll discuss about how to balance the accuracy of your model and the computational time, because this is very important in numeric modeling. For everyone, of course we want highest resolution, because in such situation you have the best details and you have better results, better accuracy, but the price is also expensive. First, let's see this. Our simulation domain actually is a stack of numerous of blocks. You can see here, if our model size is 50 blocks in length, 50 blocks in width, and 40 blocks in the vertical direction. In total, we have 100 kilo blocks, and it will consume about less than 8 gigabytes memory. That's acceptable. But if you increase the size of your model, like we higher the resolution. In the first case, for example, our resolution is 4 meters, and if we do not reduce the total area of your precinct, but we increase the resolution to 1 meters, that means you will have 200 and 200 multiply 200 in the length and width, and that's in total is over 1.6 million blocks, and it will consume much more memories. And not only the memories will be consume a lot, but also the time steps. Time steps means the time interval between each calculation. For example, if we want to predict the meteorological variation between 1 hour, for example, from 9 o'clock to 10 o'clock, if we use a time interval as 15 minutes, like let's update all the meteorological data every 15 minutes, and we only need to calculate 4 times, right? We need to calculate at 9 o'clock, 9:15, 9:30, 9:45, then 10, then we get our final result. And in total is 4 calculation. But if we reduce the time interval to 30 minutes, let's calculate every 30 minutes, we only need to calculate twice. Like we calculate at 9:30 and 10 a.m. Then we get the final result. You can see we only need to calculate twice, and this will definitely faster. But unfortunately, the time step size is not arbitrary, because mathematically time step size has to match the size of your block. So if the resolution is going up, your blocks will become smaller, and your time step will also become smaller, which means you need to calculate more times, which will significantly increase your time consumption when running your model. So you have to find out what is the best resolution for your situation. And the best way to this answer is to try different resolutions on your own machine. And I suggest you to first use the 50 multiply 50 and multiply 40 resolution in your own PC to test how long it takes to finish your simulation. And you can give an estimation about if I double or triple the resolution, how long it will take, and check if you double the resolution, whether I can say enough details of your model. So you have to try several times to find a best combination. And my experience is never let your model more than 200 multiply 200. That will consume a lot of time to finish. In my own experience, last year, I was asked to simulate the weather condition for the whole city area in a 500-meter resolution, not using MMAT, but using another mesoscale simulation models. And I was asked to simulate the weather condition within 3 months. And guess how long it takes to finish? And I have used the help of a supercomputer with over 200 CPUs running at the same time, and the simulation still takes over 1 month to finish. Sometimes that time consumption is not acceptable. So you need to keep in mind. And the next thing I want to address is to validate your model. I read here, weather forecasting is always wrong because humans in our computers, we cannot 100% accurately represent the reality. There must be some differences between the real materials and your numerical materials, and there are differences between your boundary conditions and initial conditions. What you can do here is to improve your model, make your model at least acceptable. So let me explain how we do that. In the standard simulation procedures, we do the validation by using a model to predict the past. For example, we can, after we created the precinct, we can use it to simulate the weather condition of yesterday. We let the model started as midnight of the day before yesterday and let it finished on midnight last night and for the 24 hours. And we already have the weather records for the last day for yesterday. And then we can compare the result between our prediction and the actual weather record. And you can see here on the right, on the right, you can see our model. If it look like this, you can see, oh, our model is pretty good. The result is acceptable. If your model have significant bias, we would say, oh, we need to improve our model. We need to modify some settings, like if we have input the correct boundary condition, or have we represent all the land covers in a right way. We need to check things like that. But in our simulations, in this class, we don't need to do that because we don't have history meteorological data offer you in that precinct to validate your model. But you need to keep in mind, if your purpose is to 100% to accurate to predict the weather, you have to do the validation. In our case, we more care about the difference between different mitigation scenarios. So we do not care much about that. And you can do some simple validation by directly check the output of your model in Leonardo with your common sense, whether all the values are reasonable. You can check the wind speed or humidity or temperature. Do they look like normal, or do they look similar to the weather station data that you analyzed in assignment 1? You can do some simple check to make sure your simulation is not wrong, at least acceptable. And that's all the things. And the last is some fun information about the real weather forecasting. After the previous things, you might wondering how we offering actual boundary conditions for the real weather forecasting, because we are predicting the future. We don't have the boundary meteorological data that measured on the boundaries, right? If we want to predict the temperature of Sydney in the next 5 days, we don't have the actual temperatures on the boundary of Sydney in the next 5 days. How could we make the predictions? And in the weather forecasting, the scientists would do this. They will first create a global climate model, because we are on Earth. Earth is pretty similar to a sphere, and on the surface of the sphere, we don't have the lateral boundaries, right? We don't have lateral boundaries, so we for global models, we don't have that issue. And then we use that global model to generate the weather prediction for the next 5 days. And in that model output, we go to the Sydney location and use output in the global climate model at city location as the boundary condition for our regional model. That's how weather forecasting found the boundary conditions. And as you can see, in this way, the input is not 100% accurate. That's one reason why our weather forecasting is not accurate. And another issue is how weather forecasting validate itself, because we have no time to validation. From today, we need to predict tomorrow's weather. How we validate ourselves? They have developed some ways they can do on-time diagnostics. They have some observation system. For example, today I have made my prediction of Sydney using the model for the next 24 hours. But after 6 hours, I will use these satellites and ships to do a measurement to check the difference between the prediction and the actual condition. And we use that difference and some equations to correct our weather forecasting predictions. And we create the prediction in a 6-hour frequency or 12-hour frequency. That's why sometimes you can see the outside is raining, but your phone is still showing it's clear, because it's haven't reached time the forecasting to correct itself. That's my part. The next part is Jie. Okay.
Before we move into the next part, do we have any questions for Kai? Do we have any questions regarding this boundary condition, initial condition, and all the he has introduced? Okay, if no, let me share my screen. Okay, if you can stop sharing. Yeah, then the next part, I will introduce you about the output we can get from Envi. So after every run of the Envi simulation, you will get 11 different types of output, and they are distributed in 11 different folders with the name highlighted here. And yeah, in different folders. This is the, for example, I ran a simulation last week. It is named lab test. And after the simulation, I got a folder called my project name output. And then if I open it, I got 11 different folders having different kind of outputs. And output file types, we have 2 types of output. And if we open it again, and we can see we have edt, and .edx. What is the difference between these 2 file types? EDT, it is holding the raw data, but no information on the structure of the data or of the content itself. But EDX is different, and it is required to allow a decoding and reading of the binary file. So basically what we use for Leonardo to analyze is actually, if I open it again, the EDX. Yeah, remember the EDX is used for the decoding and generating the results, and EDT contains the raw data. That is the difference between the 2 types of output files. And about naming of the output file, you can see it has 3 parts. The first part is the name of our simulation project. Basically, if you remember the previous videos, we set up a workspace, we created a new project, and we named the new project to be, for example, in this case, urban layout. And this is the project from a project name. And AT here represents the type of your output. For example, AD represents atmospheric data. Yeah, it is under the atmosphere folder, and it's represent AT representing atmospheric data. And the very last part, part number 3, time of the data. We can see here the year, month, day, and time of our simulation. And in my case, by the way, I have uploaded this lab test folder under this week's tutorial in Moodle. You can check yourself. You can download and check. I included the space file, the simulation file, and the output I got from my simulation. This space file is for a small portion of the Melbourne site. So it's not the overall Melbourne site, it's part of the Melbourne site. Yeah. And for example, if we open the atmosphere, you can see my simulation. In order to get the simulation results at 2 p.m., I started the simulation from 1 p.m. So I have the simulation results start from 1 p.m. and then I ran it for 2 hours. So I have the very last results for around 3 p.m. So I have the results from 1 p.m. to 3 p.m. And if I only focus on 2 p.m., I just analyze this specific file. Yeah, this is the way to identify the times of your simulation and what is the file you should use for analysis. And for each file, if you go to the EnviMat, this is called help page, and you can check what are the parameters included under each output category. For example, under atmosphere, we are using atmosphere as an example. Under atmosphere, we have typically wind speed and wind direction and potential air temperature and specific humidity. And also here, what we need is relative humidity and also some radiation related parameters. You should pay attention that for this latest version of EnviMat, we don't have the dry bulb air temperature anymore. We don't have the dry bulb air temperature. What we use is the potential air temperature. So this is a more accurate temperature which has considered the influence of air pressure. So remember, this is the air temperature we are going to analyze. Just choose this potential air temperature as the parameter to analyze. And we also have some vegetation related data and also the CO2 related parameters under the atmosphere folder. Yeah. And if you want to double check what is included under each category, please come to this site. You have this PowerPoint in Moodle. Please come to this site to check specifically what is included under each category. Yeah. And then we come to the requirements in A2. Outputs required in A2, the mandatory outputs are ambient temperature, which I just said we are going to use the potential air temperature, the wind speed, the distribution of wind speed, the distribution of relative humidity, and also the surface temperature. These 4, 1, 2, 3, 4, they are mandatory parameters to be analyzed in each scenario. And thermal comfort is optional. You can see here it is optional. You can choose to analyze it, or you don't need to do that. That's totally optional. And where can you extract the data for each parameter? For ambient temperature, you get it under the atmosphere folder, and the same for wind speed and relative humidity. And for the surface temperature, you get it under the buildings folder. It's a different folder. Yeah, please pay attention to this part. We get the surface temperature under a different category of the output. So this is ambient temperature and wind speed, relative humidity, and surface temperature. I will quickly show you about how to interpret the output. For example, I will just use the Melbourne part of the Melbourne site as an example. You quickly open Leonardo. Let me switch to the new screen. Okay, it is a larger screen, so you can see it up here. Yep, this is the very first interface of Leonardo, and we have different file sets. And let's just focus on file A and no comparison for the time being. Select files. We have this output folder, and let's just take a look at the air temperature. Under atmosphere, we focus on the 2 p.m. situation. We open this file. And we can see 2 p.m. is activated here. And we come to 2D and we change the data to be potential air temperature. And we want to display the XY plane, and we want the height of our map to be around 2 meters. Yeah, K equals 3, and it is equaling to 2 meters, and we extract the 2D map. Yeah, basically this is the distribution of our air temperature, and we have the legend here. If you want to change the legend or change the color, you come to the data layer legend, and you have options of changing the layer colors or the legend, the range of the legend. And also you have the special layer settings to choose whether you want to display the buildings, the vegetations, or other sources. Yeah, you can try yourself a little bit to see what if we hide the buildings. Yeah, this is the black colors are the buildings. This is the air temperature at 2 p.m. If we switch to, we also have wind direction, wind speed, and relative humidity under the atmosphere. Let's see the relative humidity at the same height. Yeah, we have relative humidity, and then wind speed. Yeah. So this is very simple, and what we require you to present in week 7 is just the reference case, and you will learn how to do the comparison in the following, in the videos listed in this week. We won't introduce in detail here about how to do the comparison. You can watch that in the videos. And let me show you about the surface temperature. If we want to switch to the surface temperature, we choose another file. It should be under the buildings, not atmosphere anymore. Dynamic, 2 p.m. and OK. And 2 p.m. ready is not different. Yeah, let's see 2. That should be 3D. It's not 2D anymore. And we want to see the wall temperature, surface temperature outside. It has 7 nodes. And from 1 to 7 is from outside to inside. And what we focus here is the temperature of the outside surface. And click OK. Yeah, if you right click, you can see if you can just right click to activate something here, or right click to disable. Just try yourself a little bit to see what is disabled and what is activated. And if you left click, you are able to adjust the settings. And if you right click, you can switch on and off. Yeah, this would be, let's turn on the legend. Yeah, the wall temperature of the buildings. Yeah, basically this is what we can use for, what we can use for analysis. And you can see if you have trees in the surrounding, and it will have shadings on the building facade, and it will have lower surface temperature than the surrounding facade, which is not shaded by the trees. You can first try to have this map, and then you can discuss with us about the specific results. And let's switch back to the PPT slides. Oh yeah, and also if you want to check the individual cell data, you can right click and see this is the Excel providing the data for the specific wall, the temperature, different parameters, for example, sensible heat, latent heat, and also the radiation related parameters. And also if you choose here, I think the time period is too short to generate a graph. If we have, for example, 3 hours, 4 hours, a bit longer, not a specific time, we will be able to see a graph here. And that was for the specific cell. Keep that in mind. Yeah. Yeah, this is the way to check the data of an individual cell. Then in the very last part, I want to highlight a few things. So basically, as Kai just introduced, we have different forcing methods, simple forcing and full forcing. You are free to choose the one you prefer. If you choose simple forcing, this is Envi guide I just opened. If we choose simple forcing, let's see what we need to adjust. Set the initial condition to be reasonable, within a reasonable range. And you can see here, this is temperature and this is relative humidity. And you can change the temperature to, for example, 16, 17. Yes, just keep in mind that you can edit the temperature here. And
鱼要烂了，泡烂了，粉都泡烂了。
Let me mute everyone. If you're not asking a question, can you mute yourself? Thanks. So if you're using simple forcing, you just manually change the temperature and relative humidity to the real situation. And the source of these two parameters would be from our the A1 weather data. You remember we have the Excel and we have temperature and relative humidity for 1 day, hourly data for 1 day. Just use that data for the simple forcing and choose the nearest station to your site. We have different stations. I remember we have 11 stations in each city, and just choose the data of the nearest station to use it as the source of the simple forcing. Or you can use full forcing. Let me show you here. Full forcing, if we go back, we choose full forcing. Next. Oh, sorry, it's too quick. Let's go back. Yeah, it will ask you to import, for example, create new forcing file. It will ask you to import either a CSV file or an EPW file. These are both acceptable weather data. And what we have provided you is EPW. If you check Moodle, yeah, if you, let me magnify. If you check Moodle under A2, we have weather files to be used in Envi. These are EPW files if you are using full forcing. Yeah, remember, if you use simple forcing, we have the weather data in Excel under assignment 1. And if you're using full forcing, we have the weather data under assignment 2 in one file EPW for each city. We don't have different stations, just one file for each city if you're using EPW. Import data from EPW and choose the I don't have the EPW here. Choose the EPW, you just download it from Moodle and check if everything is all right. If everything's all right, just make it be a Fox file, and then it will automatically be displayed here, and then you're ready to go. Close this one and click next. You can keep default as it is. We don't change the source setting and pollutant setting in the current stage. And this is a summary of your simulation information. Start from the date and time I will explain later. And total simulation time would be 2 hours starting from 1 p.m. For forcing using this EPW created Fox file. And if we click next, save and start the simulation now, we will be able to save this file. And yep, and that's all I already saved. And start the simulation. Load the project and check the simulation if you got no error, and you can run the simulation. Yeah, that's the whole procedure. The second thing I want to remind you is that really pay attention to our required date and time for a simulation. We are requiring you to have the simulation results at 2 p.m. for the given date. The given date is, is February 11th in Sydney, and February 9th in Melbourne, and February 12th in Brisbane. Yet remember to have the date and time correctly set in Envi. And in simple forcing, you can use any year because we just need to manually type in the temperature and relative humidity. There's no need to change the time, to set the time. But for full forcing, please use 2002, as we have 2002 in those provided EPW files. Please start from 1 p.m. for 2 hours to ensure the spin up time, and choose the results for 2 p.m. to analyze. Yeah. That's just an emphasis. And sample files for, you have sample files in Moodle. You have this, this zipped file in Moodle, and you can download and have a check yourself. It includes the spaces, file, the same file, and also the outputs. You can use it for exercise. My maps were generated from using that outputs exactly. Yeah. Do we have any questions? Am I still sharing my screen?
Yeah.
Yes, okay. We don't have any questions. If not, please move to the individual session, and we still have 3 videos for Leonardo listed for today. In the course outline, you can find the link for the 3 videos for Leonardo. And if you have any specific question, and please ask your tutor. And we hope you have your model ready today, and you can start the simulation. In week 7, let me check. In week 7, we will have the presentation of your reference scenario. So you don't need to do any comparison. You just need to generate the 4 parameters for your current model, and it accounts for 5%, and it's mainly for checking the individual progress. And we want to avoid any major issue before you you proceed to further analysis. So don't worry about that. That's just for a quick check. And if you have any question, please let your tutor know. Yep, all good. And you can move to the individual session if you don't have any further questions. And thank you so much, guys. Yeah, my group can stay here, and we won't change another session. And Kai's group and Samira's group can switch to Blackboard Collaborate. Yeah, you can start watching the 3 videos listed for today. And if you have any question, unmute yourself and let me know.